मैं अपना कैमरा ऑफ कर देता हूँ, मैं कैमरा ऑफ करता हूँ ताकि मैं लैपटॉप ना भूल जाए। ओके, सो वेट व्हाट, बाकी लोग हैं ना इधर?
हाँ हाँ
हेलो, हाँ ओके ओके
yeah.
yes. So yeah, so today we are going to talk about Kronecker's Jugendtraum, part 1. Jugendtraum, actually, it's a German word. It means that dream of youth. So whatever problem we are going to discuss today, it's actually Kronecker's, it was Kronecker's dream to prove this. To start, यार तुम लोग कोई अपना चेहरा दिखाओ यार, मुझे लग रहा है कि मैं स्क्रीन से ही बात कर रहा हूँ। सॉरी सॉरी, जैसे तुम लोग अपना स्क्रीन हटा रहे हो ना, तो क्या है कि स्क्रीन चला जा रहा है इधर का, मतलब मुझे दिख नहीं रहा कि कोई भी है, मुझे लग रहा है बस कि anyway, okay. So Kronecker obviously was a very famous German mathematician. One of the very famous quotes of his was, "God himself made the integers, everything else is the work of man." And what it meant to him was the prohibition of using mathematical notions and methods that cannot be reduced to arithmetic of integers. So basically what he wanted, like, he only believed in the math that actually gave you the explicit things, not just the existence. There exists something, there exists something. And one of his other principles was the rejection of actual infinity as a mathematical reality. So he was one of those mathematicians that actually at that time opposed Cantor. So yeah, I mean, that's the short talk about him. One of his famous theorems is called Kronecker-Weber theorem, which says that, it's a very famous theorem in abstract algebra. It says that every finite abelian extension of Q is contained in some cyclotomic extension. More precisely, so what is an abelian extension of Q? It simply means that an extension, in this case, a finite extension of Q, which is Galois, as well as whose Galois group is abelian. Then the theorem says that there exists an integer n, such that K is contained in Q attached nth root of unity. And this n is actually explicitly, it can be constructed explicitly as soon as you know the field K itself. So one example is Q adjoint I. It's a finite extension, finite Galois extension of Q, and since its Galois group is Z mod 2Z, it's abelian. And in this case, you can actually see that Qi itself is a cyclotomic extension. Why? Because I is fourth root of unity, right? Much like interesting example is Q is square root of -3. Again, this is like a quadratic extension. Its Galois group is Z mod 2Z, and it's again abelian. And notice the fact that the third root of unity or sixth root of unity, both of them have this square root of -3 factor there, right? So this means that Q square root of -3 is contained in e to the power 2 pi I by 6. More generally, Gauss proved the following, that the pth cyclotomic extension, which means that Q adjoined with the pth root of unity, it contains either Q square root of P or Q square root of -P, depending upon if -1 is a square mod P or not. So in general, what you can do is you can consider a number D, write it as a product of primes, and we just want to consider quadratic extension. So we can always assume that D is square free because there's a square root, so the square part will come out and it doesn't matter. So you write it as P1 times P2 times PR, and so on up to PR. Then in that case, it's really easy to see that Q square root of D is contained in, well, here the way I've written, D seems to be a positive integer, but you can always consider -D, and then you have to attach an I is like attach an I to it, and that will give you the inclusion. So q square root of d for positive or negative is always contained in q square root of p1 times q square root of p2 times and so on q square root of pr multiplied with q square q of I, right? And by Gauss's theorem, each of them are contained in e to the power 2 pi I by pi. Because I have attached this qi itself, so we can always assume that like either it's q square root of p or q square root of minus p. So this is contained in this, and which is contained in e to the power 2 pi I upon p1, p2, and so on up to pr times 4, right? So this shows that in general, if you have a quadratic extension, it's always contained in a cyclotomic extension. Well, this I hope this convinces you this theorem is true. And this actually sort of like, there is a more general construction. The whole class field theory actually is a study of all these things like abelian extensions. And in general, if you know the k and you know something called the discriminant of the number field k, then you can easily construct this n such that that number field is contained in q adjoint with the nth root of unity. Okay. So the question. So this is a famous theorem. It classifies all the abelian extensions over q, right? So a natural question arises: what if we replace this base field q by something else? So what can be said about the abelian extensions where the base field is other than q? And this is the question that gave rise to class field theory. As I mentioned before, class field theory originated from this problem, this theorem of Kronecker-Weber. The ideal goal of the class field theory is to classify all the abelian extensions of all the number fields. And this is far from being complete. I mean, no one hopes that it's going to be complete in the next 100 years or so. So not much is known about this. The only case which has been like totally classified is the case of imaginary quadratic extensions. Imaginary quadratic extension simply means that the number fields of the form q squared of minus. Oh, by the way, I'll use number fields a lot. Number fields by definition means any finite extension of q. So if q adjoint with any algebraic integer, it's going to be number field. So q squared of minus d. So we are interested in imaginary quadratic extensions, which means that the number field of the form q squared of minus d, where d is greater than 0. And surprisingly enough, the whole classification of this is somehow related to the theory of elliptic curves. So our goal is that we want to understand the abelian extensions of imaginary quadratic number fields and how these are connected to the theory of elliptic curves. Well, let's digress a bit and talk about how people, or basically Kronecker proposed himself this idea and how he came up with this idea. Okay, so one way to think about a cyclotomic extension is as follows. You have this transcendental function fz is equal to e to the power 2 pi I z. So if your z is, for example, real number, then this e to the power 2 pi I z is what? It's like cos z plus I sine z, right? And both of them are transcendental functions. So you can assume this as a transcendental functions. And to get any cyclotomic extension, what you are doing is you are attaching to q very special values of this function, right? So for example, if you want to look at like some p by qth root of unity, so when I'm saying p by qth, I mean q by pth actually. So it's like, okay. So for example, the case that we talked before, it says that q adjoint with f at 1 upon n gives you any cyclotomic extension, right? So Kronecker said, okay, what if when we change the base field from q to something else, there should exist some special functions which, when evaluated at very special values, should give us these abelian extensions of that base field, right? And interesting enough, the this idea was true. That special function in the case of imaginary quadratic extension is what's called modular J function. It's pretty well known in the theory of elliptic curves and modular forms. But what's surprising was the fact that like this whole study of algebra somehow was related to like modern number theory, right? So what is this J function? It's a function from upper half plane to complex plane, which is so-called modular. I'll talk about that later. But what I want to emphasize is the fact that it has a Fourier expansion of this form. So if you assume Q to be equal to e to the power 2 pi I tau, then J of tau has some sort of Fourier expansion whose first three coefficients are given like this. So you can think of this as a generalization of this idea, right? Because this is also a transcendental function. You have this like instead of just e to the power 2 pi I tau, you have like different values, right? Like q to the power -1, q to the power 0, q to the power 1, q to the power 2, and so on, right? And in this case, the special values will come from the imaginary quadratic extension. If you remember here, what it said was that the function was being evaluated at the special points in Q itself. So it's natural to think that in the case of imaginary quadratic extension, this is going to come from, like the points are going to come from the imaginary quadratic field itself, right? So indeed, that is the case. And we'll talk about all this in the next talk. But for today's talk, we are going to talk about elliptic curves. We are going to define J function, and we'll briefly talk about the theory of complex multiplication, which is really a very hot topic in the modern number theory. Well, the complex multiplication I'll talk about will be just related to elliptic curves, but there is a whole general theory that is which is a generalization of this in the theory of modular forms. Okay, so to talk about elliptic curves, let's start by talking about elliptic functions. It is a bit easier to understand. So what are elliptic functions? So what you do is you start with a lattice. A lattice is additive subgroup of C. It's an additive subgroup of C of this form. So it's a Z module with dimension 2. So it simply means that it is of the form z omega 1 plus z omega 2, where omega 1 and omega 2 are linearly independent over real numbers. And a function from complex numbers to this extended complex plane is called elliptic with period lattice lambda if f of z plus L is equal to f of z for all z belonging to C and L belonging to the lattice. So this is what some people call the doubly periodic function, because it's like, you know, it's periodic over this lattice, which is two-dimensional. So obviously, when you have this type of structure, you want it's just enough to consider the fundamental domain, and you want to understand such a function on a fundamental domain, right? So here is a typical look of a fundamental domain, which looks like a parallelogram, and with sides omega 1 and omega 2, right? And since what you can do at this point is you can actually compactify it, right? You can do a one-point compactification. Well, not one-point compactification, I guess. It's like realizing these sides together, you can form a torus, right? Which is a compact surface. So again, the theory of like analysis gives you that there can only be finitely many zeros and poles of this function. It's the same concept as like that you read when you have a function which okay, I don't want to go too much into detail, but the fact is that there are only finitely many zeros and poles of this function, and there's a very nice theorem which gives you the description of these. Well, gives you some idea about these zeros, like zeros and poles of such a function. So theorem says that assume that f is a non-constant elliptic function which means that it's doubly periodic with the period lattice lambda, and let these finite set of zeros and poles is given by some ai, where I is varying from 1 to say n inside this fundamental domain. Okay, yeah, so I'm talking about everything about like fundamental inside fundamental domain, because that is where we want to consider this, right? And let mj, well, mi denote their orders. So for poles, it's going to be negative. Then we have that summation sum over all the orders is going to be equal to 0. And not only that, if you sum the orders with the AIs itself, so sorry, it should be MJAJ, it's congruent to 0 mod the lattice, which means that this sum is going to be an element of the lattice. Well, to get this, what you do is you integrate over a shifted fundamental domain so that you avoid like poles and zeros on the boundary of the function. Here. So for this, you want to integrate over this parallelogram the function f itself. And for this, what you want to do is you want to integrate the function, instead of f, its logarithmic derivative. When you do that, you will find these two conditions. So first condition actually gives you something very interesting. If you are counting multiplicity, this gives you that the number of zeros are equal to number of poles, right? Because there are some positive terms that are coming from zeros and some negative terms that are coming from poles, and they are canceling out each other, right? And this number n is called the order of the function. And f, in this case, turns out to be an n-to-1 map, counting multiplicity, obviously. Which means that given any point that it is achieving, it's going to achieve that at n points. Not distinct, but like there's a concept of multiplicity when you write it's I guess power series, like not, yeah, power series expansion, it starts at something like z minus that point to the power some k, and that k is the order. So this. Okay, so yeah, we'll discuss some examples, but before that, any questions? Okay, yeah, so let's go ahead. So I'm going to talk about two very special kind of elliptic functions, and actually they are really like the base of the whole theory like that goes into elliptic curves. So the first example is Vesta's p function. It's defined the following way. You start with a lattice lambda, and then this p sub lambda of z is defined in the following way. It's equal to 1 upon z square plus summation over the lattices, non-zero lattices of this 1 upon z minus omega squared minus 1 upon omega squared. Notice that this function is analytic on c mod the lattice, not mod, c minus the lattice. And it has poles at the lattices, as you can see from here, right? Of order 2. There's a square here. So the poles of order 2 at lattices. And notice one thing, everywhere there's a square. And the thing is, like, if omega is an element, then minus omega is also an element. Using that fact, I mean, element of the lattice, using that fact, you can show that it's an even function. Right? Okay. So what we can do now is, to get another example, we can differentiate it, right? So when you differentiate it, you get a function like p prime. We denote it by p prime sub lambda of z. It's like this, minus 2 times summation omega belonging to the lattice. You can see that this term goes away. So you can consider like all the rows. So it's like 1 upon z minus omega whole cube. In this case, this is also analytic on c minus the lattice and has poles at the lattice points. But in this case, the order is 3 for obvious reasons. We are differentiating a function whose poles are of order 2. So obviously, the derivative will have poles of order 3. And notice in this case, it's an odd function. What this gives you is that suppose the lattice is of this form, z omega 1 plus z omega 2, then this implies that at the center points, like the center points of the parallelogram, so omega 1 by 2, omega 2 by 2, and omega 1 plus omega 2 by 2, all these values are going to be 0. Why? Because, well, p prime of omega 1 by 2 is going to be same as p prime of omega 1 by 2 minus omega 1 by 2. Sorry, okay, let's write down one case. It's basically, this is implied by the fact that something like this. Omega 1 by 2 is actually equal to P prime this of omega 1 by 2 minus omega 1, right? And this is, well, it turns out to be minus P prime of omega 1 by 2, right? That gives you that this is 0. Similarly, other points. And the thing is, its order is the poles are of order 3, and we got 3 distinct points where it is 0, right? So what it tells you is that omega 1, omega 2, and omega 1 plus omega 2 by 2 are simple zeros of P prime. The simple part is really important. Okay. And this actually also gives you, since this is like simple zero of order, like simple zero of P prime at these points, it also gives you that P cannot have zeros at those points, right? So what it tells you is that, yeah, so, or like the point is, what I'm trying to make here is that at these points, P cannot have same value itself, okay? And that will be useful later. Okay, so I wrote everything till now, so now I have to write it. Okay, so till now, any questions? No? Okay, okay. So, okay, so what we can do at this point is just looking at the poles and zeros of these two. We know that there are poles at lattices of different order. We actually want to use a similar technique as like generally we use in analysis, like complex analysis, the Liouville's theorem. So look at this function or the ratios of these functions. So you look at this P prime Z squared. So for time being, I'll not use the lambda. It's clear, like we are considering a fixed lattice, and divided by the following: P of Z minus P of omega 1 by 2, and P of Z minus P of omega 2 by 2, and P of Z minus P of omega 1 plus omega 2 by 2, right? And let's notice. So, okay, let's look at the poles. The numerator has poles at the lattice points of order 6, right? And if you look at the denominator, it also has poles of order 6 at the lattice points, right? And if you look at the, we already know that the zeros of the numerator are at omega 1 by 2, omega 2 by 2, and omega 1 plus omega 2 by 2, right? So the way we have constructed the denominator, it turns out that the poles and zeros cancel out. So it gives you that this particular function doesn't have zeros or poles. So now we are inside this well, a fundamental domain which I talked about. You can think of as like a compact surface. This gives you that this function is going to be constant, right? And it turns out when you compare the coefficients of like their expansion, it gives you that this constant is going to be equal to 4. Okay, so when you rearrange and do everything, like evaluate P at omega 1 by 2 and all these values, you'll get a equation like this. Write it down. So obviously 4 is going to be there, then P of Z cubed minus G2 of this times P of Z minus G3 of lambda, right? And as I mentioned before, these values are not same. So it tells you that whatever polynomial that we got on the right hand side in terms of P of Z has distinct roots. And whenever a polynomial has distinct roots, its discriminant is always going to be non-zero. Okay, that is one thing that you might want to keep in mind. And where these, let me write down explicitly what these G2 and G3 are. So they are actually special values of what's called the Eisenstein series in the theory of modular forms, but we don't need to understand that here. We just need to know its structure. So G2 of lambda, it depends upon obviously the lattice. This is actually going to be equal to 60 times this thing. of 1 upon omega to the power 4. So, okay, so this also implies that if you consider any other lattice of this form, and you take any lambda belonging to complex numbers, then this is actually equal to well, G2 of this thing divided by lambda to the 4, right? And similarly, similarly, if you have G6 of lambda, this is actually equal to, so let me put it here, times omega belonging to lambda minus omega belonging to the lattices, non-zero lattices of 1 upon omega to the power 6. And also this also implies that if you have something like this, then that is actually equal to okay.
But
Okay, so
to see that the coefficient of pz square is 0.
Pz, yeah, it turns out that the coefficient of pz square is 0 in this case.
Okay.
Yeah. This is the special form that you get for any lattice, which is a very nice thing for us because this is the form that you want to convert things when you want to solve like a cubic, right? So yeah, sometimes this is really helpful. Okay, next question. So okay, so yeah, so what it gives you is that if you want to consider this in terms of algebraic geometry, it tells you the following, that this pair P of z comma P prime of z, this satisfies a polynomial which is of this form, 4x cubed minus g2 is x minus g3 of this, right? And one good thing about this is this polynomial is that this, if you call this as say f sub lambda of x, then we have that the discriminant of f sub lambda of x is non-zero. Anyone who wants me to remind what discriminant is basically? It's just going to be, if you have root, say lambda 1, lambda 2, lambda 3, then this disk is just going to be equal to, basically you look at the product of lambda I minus lambda j square product over I not equal to j. Okay. Well, with some rearrangement plus minus depending upon, like, this is not a precise definition, but this is what matters. That depends upon the root. It is 0 whenever it has repeated roots. Okay, actually this particular equation leads us to our next topic, which is elliptic curves. I'll go over that briefly. So use a different color. Okay, so next section, elliptic curves. Okay, so for time being, we'll focus our attention just when the base field is just complex numbers. But in general, all this theory will be true as soon as you have a field whose characteristic is not equal to 2 or 3. Okay. So what is an elliptic curve? Elliptic curve is a projective variety. Simply means that it's as something called an irreducible set inside P2 whose affine projection looks something like this. Looks like, so let me do it like this. Elliptic curve defined over K is of this form, y square is equal to fx, where this is a cubic. Okay. So what this means, that the affine projection looks like this, it simply means the following. it satisfies in projective plane, it satisfies an equation of this form. So, well, it will look something like this, like I guess x cube plus a1 times x square z plus a2 times x z square plus a3 times e cubed, right? And then what you do is there are two possibilities for z. It can either be 0 or is not 0, right? Whenever this is 0, what do we get? We get that the only possible value that can be anything but 0 is y. So we get something like this point in projective plane. So keep in mind, in projective plane, point means a line. All the lines where y can vary. So yeah. And if z is not equal to 0, we can divide throughout by z, and we actually get y square is equal to fx, where y is actually equal to capital Y divided by z, and x is actually equal to capital X divided by z, right? So keep one thing in mind. These x and y are like coordinate functions, which are not like the normal x, y. These are the functions which are like sort of representing at this point, they are representing infinity. So these are very special functions. Well, using Riemann-Roch, you can show that this x and y have poles at infinity of order 2 and 3 respectively. Anyway, and we also want something extra actually. Yeah, cubic with the discriminant of fx is non-zero. This gives you the smoothness condition if you want to talk in terms of, I guess, algebraic geometry or some sort of geometry. Okay, so we already have seen a good example of such a curve, right? This curve that is being satisfied by P and P prime. Okay, so you can think of it the following way. So we can define a function from the fundamental domain of any lattice to this particular elliptic curve over C, which is defined the following way: x comma y, which satisfies, well, let me write it this way. And I'm being a bit sloppy because, well, ideally you should define it in like projective plane, but I'll explain what happens to one extra point. X minus okay. So what happens is the following: what you do is you send any g like z to this point p z comma p prime z. Okay. More precisely, if you want to look at in terms of like projective plane, it is following: you are sending any z to the following point whenever z does not belong to the lattice. And there is one, since we are boarding out with the lattice, there is just one point, lattice. So if z belongs to the lattice, well, I'm saying, okay. So when I'm saying z belongs to the lattice, is actually z is the lattice because of the structure of this, right? Any element of this form looks like some complex number plus a lattice, right? So what I'm saying is that z is if z is 0 mod lattice or not. If it is it belongs to the lattice, then you send it to the following point. Okay. Any questions? Okay. So this is some like a brief introduction to, so what actually, okay. So this gives you that if your elliptic curve has this nice form, then that elliptic curve is actually coming from some sort of lattice, right? And we have this explicitly how this lattice looks like, right? But in general, I'm not going to prove this, but in general, you have that if your characteristic of the base field K is not equal to 2 or 3, which in this case it is, right? So we are, everything is over complex numbers whose characteristic is 0. Then in that case, every elliptic curve can be written in this form. So it tells you that over C, every elliptic curve over C is coming from some lattice. So it looks like C mod some lattice, right? So in like the analytic definition of elliptic curves actually comes from here. So this is C mod lattice is isomorphic to a torus, right? So that's why sometimes people say that elliptic curve, by definition, they define in the following way. Elliptic curve is a smooth projective variety of genus 1. The genus 1 is coming from this fact that it's in like its picture looks like a torus. Okay, so over C it's pretty easy, at least to understand this. You just want to understand C mod a lattice, right? So throughout the talk, I'll generally, whenever I'm considering elliptic curves, I'll be considering C mod a lattice. Okay. So for our purposes, we want to understand the endomorphism ring of these elliptic curves. And why is that? Because actually endomorphism rings of elliptic curves, I'll define what that is, basically maps between elliptic curves. That is where this imaginary quadratic extension coming into play. Okay. Okay. So the next section. Any questions before this? Feel free to interrupt me at any point. Okay. Endomorphisms of elliptic curves. Okay. So by definition, if you have two elliptic curves, E1, C mod lambda 1, and you have E2 equal to C mod lambda 2. Then by an endomorphism, by a homomorphism of between E1 and E2, it simply means that a map from E1 to E2 such that it's an analytic map. So let me call this analytic take such that phi, when evaluated at 0, it's actually a 0 element here. It simply means that. But I'm not going to go too much into details. This is equivalent to the following: that there exists a non-zero, and okay, and A belonging to complex plane, so it can be, well, I mean, it can be 0 or non-zero. Well, when it is 0, it's a 0 map, such that A times this first lattice is contained in the second lattice, and phi of z plus lambda 1 is actually equal to az plus lambda 2. It's always going to be of this form. This is an equivalent condition. This also can be used. And obviously the definition of isomorphism is simply that if there exists an inverse map such that when you are composing in any direction, it's going to give you the identity map for each of these. Okay. And the set of all homomorphism we define the following way. So we call it hom E1 comma E2. This simply means that all the maps from E1 to E2, all the, well, these special maps from E1 to E2. Okay. So actually this definition gives you following, gives you that if you assume E1 and E2 to be the same elliptic curve, then this homomorphism is denoted by endomorphism of E, and this is actually equal to all the A belonging to, so this is going to be isomorphic to all the A belonging to C such that A of this is contained in this. Such that when you multiply A to a lattice, it's inside the lattice itself. Okay, assume that, sorry, remember that these, we are assuming, so these are the additive subgroups. So like multiplying with some element of C is not always going to be inside the lattice, right? I'll give you an example, but this follows directly from these two facts, right? This is what exactly it is, and well, this is the condition that automatically follows. Okay, so let me give you an example. What I was trying to say is the following. If you look at the, for example, the endomorphism ring of say C mod this following lattice, right? Third root of 2, say. Then what do we have? This is isomorphic to A belonging to C such that A times this lattice is contained in this lattice again, right? And what is this? So every element of this looks like some A times B third root of 2, where A comma B belongs to Z, right? Well, I should use some other, okay, yeah, use well, I'll use E1, E1 comma E2, right? So this actually forces the following. Because of this has to be contained here. We have that A has to belong to 1 comma third root of 2, right? So this already gives you a lot of restriction, right? And it also gives you the following, that A times third root of 2 is always going to be inside this, right? Well, if you just look at these two conditions, it actually forces that A can only be an integer. So it gives you that this is isomorphic to just Z. So as you can see, there is a huge restriction on the values of A that can be attained because of this extra condition. Okay. And in general, in most of the cases, it turns out that the endomorphism ring is going to be isomorphic to integers, Z itself. But there is a very special case, which I'm pretty sure you can guess where this is not going to be Z, which is the top of the, like the reason we are studying the endomorphism rings. And that is going to be coming from imaginary quadratic extensions. Okay. So we have the following preposition. So it gives you the following. So you consider an elliptic curve of this form, and let R is equal to the endomorphism ring of E. Obviously, this is contained in C by definition. Then we have the following two possibilities. R can either be equal to Z, or R is an order of an imaginary quadratic extension. Basically, okay, so any order of imaginary quadratic extension, for time being, assume that it's going to be an ideal of an imaginary quadratic extension. Okay. Extension, and this lambda that we are considering is also going to be proportional to an ideal of R. Wait 1 second. Sorry, proportional to an ideal of R. Okay. So I was a bit sloppy there. So the thing is, like, you're talking about imaginary quadratic extensions. That's a field, right? So it cannot have ideals, non-trivial ideals at least. But what you do is you look at something called its ring of integers. You're looking at all the elements which satisfy a monic polynomial, and that actually forms a ring. Now, this tells you is that this R is going to be a submodule of that ring of integer. Not only that, this lattice is going to be proportional to an ideal of R, because any submodule of a ring is also going to be a ring, and so it has the concept of ideals, and it just says that this thing is going to be proportional to an ideal of R. Okay. So I'm not going to prove this, but I'm going to do an example. Okay. So one example where this is the case I already did here. One example, the other example that I would like to do, which actually falls in this category, is the following. If you consider your lambda to be equal to, say, 1 comma I. Wow, sorry, my laptop is doing something. Okay, right? So one thing you notice that it belongs, like it is contained in where? It's contained in Q of I, right? Because by definition, what this is Z adjoined with I, right? So this is contained in, like, not, this is contained in Q of I. Not only that, actually, it turns out that for Q of I, this is the ring of integers itself, right? And in this case, let's look at this. So what do we know? We know that, well, by definition of R, what is R? It's going to be all the elements of alpha, all the elements alpha in C, such that alpha times 1 comma I is contained in 1 comma I, right? So what do we know? We know that since, and the point is that 1 belongs to R, and not only that, if you look at the following, if you multiply by I, 1 comma I, what do you get? You get, well, I comma minus 1, which is same as 1 comma I. So it tells you that I also belongs to R, right? So this gives you that 1 and I belongs to R. So in particular, this R contains 1 comma I, but at max it can be 1 comma I. So it is exactly going to be 1 comma I. Okay. Or you can, if you want to write it, it looks like this. This makes it look much more simpler in the sense that it explains this. It's going to be an order of imaginary quadratic extension. It's actually the maximal order, because it's exactly equal to the ring of integers. Okay. And you can see that this is so this sort of gives you the connection how quadratic extensions are coming into play. Okay. And here's a definition. An elliptic curve E, which is equal to C model lattice, is called elliptic curve with complex multiplication in short we call it CM. The elliptic curve is CM if the endomorphism ring of E is not isomorphic to Z, which means it's of the second case. So I didn't want to write like that. It's an order of imaginary quadratic extension. I'll just keep it like this. If it is not Z, it's over C. If it is not Z, it's going to be something else. The story is a bit different when you are considering all these concepts we have discussed till now over finite fields or any field of characteristic prime. Okay. Any questions so far? Karthik, how much time do I have? Like 10 minutes or so? Or should I end right now?
Up to you.
I mean, it's up to you guys, I guess. I just want to briefly talk about like J, oh, not actually, it's not a brief, but yeah, I want to talk about J invariant, but yeah, I mean, I can stop here, I guess.
I have a question. So,
Mhm.
so endomorphism group can can we say that then the order of the endomorphism group can be, I mean, not order. Is it a group free group of Z generated by two elements always?
No, no. So this is what it shows, right? It says that it's either okay. So this precaution you can think of it the following way. If the order of the yeah, so if it is a one-dimensional, I mean the free group over Z of dimension one, it's always going to be equal to Z. If it is of order two, it's always going to be an order of imaginary quadratic extension. So this simply means what? It's like Z omega one sort of thing, right?
Right.
And this is the case where you have like Z omega 1 plus Z omega 2. Well, don't confuse this omega 1, omega 2 by the omega 1, omega 2 of lattice.
Right. Right.
So maybe I should use Z lambda 1,
Yeah.
Z lambda 2. Does that make sense?
Yeah. But that what I meant is this. So basically, it can be a free group of order at most two, right?
At most 2, yes. But this is over C.
Right.
Over any field of a characteristic prime P, so P, in that case, it can have three possibilities. Either it will be equal to Z, or it will be equal to an order of imaginary quadratic extension, or it's going to be what's the word? A quaternion. Yeah.
Okay.
Any other questions? Okay. So just give me 5 minutes. I'll just finish this, or I'll try to do how much ever I can. Okay. So till now we discussed about like elliptic curves. Whenever we're talking about a class of elliptic curves, you want to classify the isomorphism classes, right? So for example, if you have, for example, an elliptic curve whose algebraic equation looks something like this, and there's another elliptic curve whose algebraic equation, for example, looks like this. You can easily check these don't have discriminant zero because none of the roots are repeated in over complex. In this case, for example, here, can you say that these two elliptic curves are isomorphic over C? Well, in this case, you can easily say, right? For example, if you send x comma y to third root of 2 of x and then square root of 2 of y. If you do something like this linear change of variable, or maybe like rescaling, it actually gives you that any element will, okay. Yeah, well, it's okay. When the other way around, I guess. This gives you a map from here to here. Why? Because when you put these values, what does this become? This equation actually becomes like 2y square is equal to 2x cubed plus 2, right? Which is same as saying, well, y square is equal to x cubed plus 1, right? So like in this case, it is easy, right? So sometimes it is easy, but for example, what if you have something like this? X cubed plus x, say, and here you have y square is equal to x cubed plus 2, for example. Can you say that these two are isomorphic? And or you can say that these are not isomorphic. Or I mean, can you give something very concrete that actually can give us this, like these two elliptic curves are isomorphic or not? Right? There is a tool which is the J invariant itself. So there is an invariant of modular forms. It's called J invariant that actually classifies all the elliptic curves over all the isomorphism classes of elliptic curves over complex numbers. So let me define it. Okay, so if you have an elliptic curve, E lambda, which by definition is equal to y square is equal to 4x cube minus, okay, so my laptop is freezing, minus g2 lambda x minus can you guys hear me? Okay, okay.
Yeah.
The thing is like my pen is either my pen is stops working or there is some issue with the laptop or something. In this case, what you do, it turns out the discriminant in this case of the right hand side, let me denote it like this, it turns out to be something like this, g2 of this cubed minus 27 g3 squared, and this is not equal to 0. We have discussed this earlier, right? So the J invariant of this lattice is defined the following way. It's equal to 1728 times g2 lambda cubed divided by delta of this lambda. Okay, and it turns out that whenever two lattices are isomorphic, which is same as saying that two elliptic curves are isomorphic, in that case the J invariant of them are going to be equal. Okay, well, I wanted to prove this, that, well, but let me just put the statement there. Well, this is just for sake of completeness, just as a theorem. Over C, comma J classifies or prism classes of elliptic curves. Okay, and as I mentioned before, that this is really like connected to what's called like our question about solving the similar result as Kronecker Weber in the case of imaginary quadratic extensions. It turns out that this J function, when evaluated at very special values coming from imaginary quadratic extension, so this you saw, it's like a transcendental function, right? An amazing fact is that whenever you evaluate this J value at very special values of this imaginary quadratic extension, the so-called Higner points, then that turns out to be an algebraic integer, which means that it satisfies a polynomial with the leading coefficient equal to 1, which is really something very amazing, right? You have a transcendental function and you evaluate at a very special value and it gives you an algebraic number, not any like any number, any algebraic number, right? So yeah, I mean, that was something I found really fascinating, so I want to tell you guys. But yeah, we'll stop here. Hopefully this talk was interesting.